Hey, hello, and welcome to our lesson on microscopic muscle anatomy and muscle physiology. Is in week 9 of your quiz information. And what you want to do is pull up or print out this page from your module, from module 4, so that you'll have this with you as I go through the information that we're going to learn today. So I'm going to start with our PowerPoint. And here we go. So when we take a look at a muscle, and then also you want to pay attention to the APR code, which we will be taking a look at some of the things within the APR as well. So if we go through the definitions that we have on our list, there's a couple more in here that are not on your list. So I'm going to need you to add one of the terms. So let me get my pen. Okay, so sarcoplasm is the same as the cytoplasm, but we don't really care. We don't need to know that. We've talked before a couple of times in different places that skeletal muscle cells have multiple nuclei, so you can remember that, but we don't really need to worry about how they formed. Okay, so the term that I need you to add to your list, now that I see that it's not there, it should be there above myofibril, is sarcolemma. So that's another name for the plasma membrane. So we'll take a look at that in a minute. Now, because it's the plasma membrane, it's going to have chemically gated and voltage gated channels along its length so that you can carry out an action potential, just like in a neuron, or what we've talked about before with membrane channels. Okay, so voltage gated channels and chemically gated for that matter. Okay. Now, also, we're going to notice that in the sarcolemma, we have these transverse tubules, or we call them T-tubules, that are going to extend deep into the cell, and I'll show you a picture of that. And they also contain voltage-gated channels, but they're going to be for calcium, and we'll explain why they need to be calcium in a moment. So when we take a look at this picture, here is the sarcolemma. You can see, I'm just going to write on it bigger. And that will surround the entire muscle fiber. So this, like it says right here, is one skeletal muscle fiber. And then we have little holes that are poked into the sarcolemma here. And each one of those little holes is going to be connected to one of these green lines right here, which is our T-tubule. So those are openings, like it says, openings into the T-tubules, and then the T-tubule will be all of these green. So we can see T-tubule right there. So they're going to extend down into the cell, and they're going to come in contact with every single structure inside of a muscle cell called a myofibril. So the myofibrils are like bungee cords inside of the cell, and their job is to do the contraction of the cell. So just like you want to have a bunch of team members on your tug of war team, so a muscle cell wants to have a lot of myofibrils inside of it, because that is where the energy, or where the contraction, is generated from. So when a muscle shortens, it's going to shorten along the length of the myofibril. And it's the organization of the myofibril that gives it its light and dark bands, or the striations, that we associate with skeletal muscle. So covering over every myofibril, we are going to have a structure that looks all webby like this called the sarcoplasmic reticulum. So that is the blue webby stuff. I know that's so technical. Blue webby stuff. And that is going to cover over, it's like a sleeve that covers over every myofibril. And inside that sarcoplasmic reticulum, because the SR is how we abbreviate it, is the same as the smooth endoplasmic reticulum. One of its jobs is to store calcium. So that is its function within the skeletal muscle fiber, is to store calcium until it's necessary for muscle contraction. All right, now when we take a look at this banding pattern that we see along the myofibril, and all of the bands all line up on all the myofibrils, so it's all light in the same area and it's all dark in the same area, and light and dark and light and dark as we go all the way down. So it's organized into these repeating units called sarcomeres, and we'll look at sarcomeres in a little minute. And in the sarcomere, you will see all the different bands that you see on your list, and H band and or I band and A band and Z disc and H zone and M line. So we'll get to those in a minute, but first we want to go to a bigger picture of the sarcomere. But on our way there, we are going to go to what the relationship between the sarcomere, the sarcolemma and the T-tubule. So we're doing the sarcolemma and the T-tubule. So here is the sarcolemma. This is the cell membrane. It's a phospholipid bilayer, and you can see it's polarized, so it's positive on the outside and negative on the inside. We're going to have voltage gated sodium channels, voltage gated calcium channels, potassium channels in it, and then we're going to have this voltage sensitive calcium channel and then a calcium release channel. That's inside. This is the sarcoplasmic reticulum, this big blue thing right here. So when a sarcolemma depolarizes, when it gets a signal from the motor neuron and the acetylcholine binds to the chemically gated sodium channel, that's going to then open up the voltage gated sodium channels, and then that's going to depolarize all the way down the membrane, just like you learned in membrane potentials. And so when it gets to the voltage gated sodium channel, that will open up, the sodium rush in, and then eventually the potassium channel will open up and it'll repolarize. But instead of just passing down the membrane, when it comes to a T-tubule, it's going to go inside of the cell. And so if it's depolarizing from the other direction, it's going to go down inside of the cell. And when the T-tubule depolarizes, it's going to cause these voltage gated calcium channels to open up. And when they open up, they're hooked to this calcium. They're actually mechanically attached to this calcium release channel. And when they open, then the calcium is going to leave. So this little gate opens, and the calcium that's stored within the sarcoplasmic reticulum is going to leave and enter the cytosol of the skeletal muscle fiber. So we'll talk more about that in another video. So the myofibrils then are bundles of myofilaments, which are the contractile proteins. So we can say myofilaments are in the next picture, contractile proteins. I'm writing this for no reason because it's in the very next slide. We'll just put that right there. Okay, contractile proteins. And then the myofibril will be surrounded by the sarcoplasmic reticulum, and there can be hundreds up to thousands per cell. The more muscular you are of a person, the more myofibrils you have. So as you work out and your muscles hypertrophy or get larger, it's not because you're getting more muscle cells, because you're born with all the muscle cells you're ever going to have, but it's because you are increasing the number of myofibrils due to the amount of force that you are applying to the muscle. So if you are always lifting something heavy, your muscle doesn't want to use all the muscle fibers all at once to try to lift that heavy thing. And so it will start building more myofibrils in order to accommodate that weight. So the more you work out, the more myofibrils that you'll produce. But when you stop working out, your body eats the myofibrils because it doesn't need them anymore because you're not lifting weights anymore. Okay, and then like we said, the sarcoplasmic reticulum is the same as smooth ER, and it's going to contain calcium, contains calcium pumps that import calcium and calcium release channels. So not only are we going to release calcium, but then when we're done, we're going to pump it back into the sarcoplasmic reticulum as well. Okay, so the myofilaments are the contractile proteins within myofibrils. We have two types of myofilaments. We have thick filaments, which are bundles of myosin proteins. So if you look on your list where it says thick filament, it says myosin. We'll look at that structure in a minute. And then thin filaments are two twisted strands of actins, which are little circle proteins that are twisted together into two strands of actin. We don't really care about F-actin. This is the chain, and this is the individual subunit. But on each one of the actin molecules, there's going to be a place for myosin to bind to called the myosin binding site, where the myosin head's attached. I'll show you that in a moment. And then there are two other proteins associated with the thin filament besides the actin. There's tropomyosin and troponin. And their job is to act as regulatory proteins that prevent the muscle from contracting when we don't want it to contract. All right, so in this picture, we're going to take a look at the thick filament. So each one of these yellow molecules is called a myosin molecule. And a myosin molecule is made up of a tail with two twisted strands. And then the heads, we have two heads. And on each head, we're going to have an actin binding site where these red circles are going to bind to. And then we have an ATP binding site where an ATP molecule is going to bind in order to give the muscle its the myofibril its contractile ability. Then in the thin filament, here we have the G actin are the little circles. The F actin is just the whole chain of them, or the filament that the chain will be hooked together. But we're just going to call it actin. So we have two chains of these red actin molecules that are twisted around one another. And if you notice, there are these black spots on each one of the actin molecules called the myosin binding site. And that's what this actin binding site on the myosin head is going to bind to on the red circle, actin. Then to make sure that the myosin is not binding to the actin right now is this green protein called tropomyosin. So it's covering all of the myosin binding sites on the actin. And when it's time to move the tropomyosin out of the way so that muscle contraction can happen, we have these little handles called troponin, these little blue things. So there's 3 troponin molecules, make this little complex, and calcium will come in and bind to each one of these. And when it binds to each one of these, it changes the shape of the green molecule and pulls it out of the way. So tropomyosin is there to prevent myosin from binding to actin when we don't want it to. And troponin is the handle that when calcium binds to it will pull the tropomyosin out of the way. So now we're going to go back to the sarcomere information. So those were the alternating or repeating light and dark bands. So a unit of light and dark band that repeats all the way down the myofibril called a sarcomere. So it's going to be composed of overlapping thick and thin filaments. And the ends of the sarcomere are known as Z discs. So I'll show you that. And they're going to be made up of proteins that run vertically through the cell instead of horizontally like the myofilaments do. And it anchors the myofilaments in place. And then the positions of the thick and thin filaments within a sarcomere are going to give rise to the alternating light and dark, or I bands and A bands. So the I band is the light region, and it's only going to contain thin filaments. And because it only contains thin filaments, it's not as thick, and so it's not as opaque, and so light is able to pass through it better. And so that is our light appearing region. So we can say the I band is the same as the light band. And they get smaller. Oh, they're bisected. So running right down the middle of an I band is going to be a Z disc, which is the edge of a sarcomere. I'll show you a picture in a moment. And the I bands will get smaller when the muscle contracts, and they can actually totally disappear if the muscle is maximally contracted. The A band, on the other hand, is the dark band. And the reason why it's dark is because it has both thick and the portion of the thin filaments that overlap the thick filaments. And within the middle of the A band, we're going to have an H zone and an M line, and it's the region that's in the middle of the sarcomere. So if we look at that, so we'll look at this really quick right now. So here is my sarcomere from Z disc to Z disc. So if I want another sarcomere, it's going to be Z disc to Z disc and Z disc to Z disc and Z disc to Z disc. So each one of these is a sarcomere, sarcomere, sarcomere. All right, now we can see within the sarcomere that we have an A band. This is dark. And we'll show a close-up of it in just a minute. And that's going to have both the thick and thin filaments in it, so it's going to be dark. But in the very center of it is an H zone. And the H zone only has the thin filaments. So if we draw a myosin molecule, like this. And then we have myosin molecules that go the other way in a sarcomere. The H zone is going to be this area right here that just has the tails. And then the tails are going to be linked together by little linker proteins. So this is our H zone. And then these linker proteins are all going to line up and they're going to form a line in the middle of the H zone known as the M line. Okay, so it's a protein meshwork. It's the attachment site for the thick filaments. So there's the M line. But again, we're going to show you it magnified in a minute. So now if we go out to the I band, this is the light portion. So how do I remember that? There's an I in light and an A in dark. Okay, so that's not what it really means, but that's how I can remember that. So then the I band is only going to have thin filaments in it. And you can see here's my Z disc, and there will just be thin filaments attached to it. So if we magnify this even more, here is one sarcomere from Z disc to Z disc. So if we look at the thin filaments, we can see how the thin filaments alternate as they're attaching to the Z disc. So in this sarcomere, here's one thin filament, 2, 3, and 4. And then the other side, we're going to alternate. And so this one only has 3 thin filaments on it. And if we look over here, here's thin filament, thin, 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 attached to this zigzaggy line called the Z disc, and then thin filaments over here on the other side. So the thin filaments are going to project towards the center of the sarcomere. So they're going to move in this direction and this direction. And as a muscle contracts, they will continue to be pulled towards the center of the sarcomere. And they will be pulled by the thick filament. So where's the label for the thick? Oh, there it is. Okay, so the thick filament is this whole yellow or gold colored thing with the little heads that are sticking out. And these heads are going to reach up and grab onto the little red circles of the actin molecules of the thin filament and pull the 2 thin filaments towards the middle. So this area in the middle of the sarcomere where the thin filaments are not touching one another is the H zone. And so this is what's going to disappear when we have maximal contraction. We should not see a thin or an H zone anymore when the thin filaments come together. And then the M line is what's holding these thick filaments in the center. Then the thick filaments are also attached to the Z disc by what are known as connectin proteins. We also used to call them titin proteins, but I don't really care that you know that. So, okay, so that's everything in the sarcomere. If we go to a myofibril and cut little sections in the different parts of the sarcomere, if we go in the H zone right here in the middle, we should only see thick filaments. And yep, that's all we see in the H zone. In the A band, we should see overlapping thick and thin filaments. And in this picture, when we take a look at it, it looks like we just have thick filaments reaching up and their myosin heads grabbing onto the actins, but they also grab down here. And so these guys will both pull on this thin filament. But then, because we're only in 2 dimensions, we can't see what's coming out of the paper, out of the screen, and what's going into the screen. So that's why this is a really valuable representation of what's in the A band, because here is every myosin or every thick filament. And then look at thick filaments are completely surrounded by thin filaments so that we can maximize the force of contraction that's going to occur when the thick filaments are going to pull on the thin filaments. Then the I band, because the I band is only going to have thin filaments in it, here are the thin filaments, these red things. And then these connectin proteins are what are holding on to the thick filament from the other side. Okay, so that should give you a good comprehensive understanding of the parts of a muscle fiber. So this is one muscle fiber is going to have all of these parts, but there's some other things, few other things that we need to know. So I'm going to have you add something else to your list for this week is motor unit. So a motor unit is a motor neuron and all the muscle fibers it innervates. And so here I have 2 motor neurons. I have motor neuron 1, whatever color that is, blue. This is the blue one. And then motor unit 2, which is the red one. And if we look at what they're connecting to, you can see that this motor or muscle fiber and this muscle fiber are part of motor unit number 1 and motor unit number 1. And then the red ones, so that this muscle fiber, this one, and this one, all the ones that are colored red, are part of motor unit number 2. Now, if we notice that this one only has 2, so this is 2 motor neuron or muscle fibers. This has 4 muscle fibers. Now, does that matter? It absolutely does matter. So this would be known as a small motor unit. And so would this one. But if I had more, like if I had 1,000 muscle fibers in it, then that would be a large motor unit. And they're going to do, large motor unit, and they're going to have different jobs, which we'll look at now. So a small motor unit have less than 5 muscle fibers and allow for precise control over force output. So very delicate movements. They're going to be going to your fingers, muscles of your fingers, toes, and face. So that you, and eyes. So that you have very delicate, precise movements. Large motor units, though, have thousands of muscle fibers, allow for production of a large amount of force, but not precise control. So some of our muscles that have large motor units in them would be the gluteal muscles, the pectoral muscles, the quadriceps. So those muscles, we don't need to move things very delicately. We just need to create a tremendous amount of force. And so one motor neuron will activate 1,000 muscle fibers all at once. So you can't help but produce a lot of force with that. But by the same token, you can't have a lot of control over it either. All right, so make sure you know the difference between small motor units and large motor units, and then the definition, of course, of a motor unit. Okay, then we're going to go on to just a little bit of muscle physiology for this. So the first thing is, if I stimulate a muscle in order to get some muscle fibers to fire, and then we're going to only fire as few as it takes to overcome the force or to match up with the force or the stimulus that was applied. So we're going to stimulate the muscle right here. We're going to go through a little period of time right here known as a latent period, and it's about 5 milliseconds long. And during that latent period, that's when the signal is coming into the cell. So the sarcolemma is depolarizing, and it's going down the T tubules, and it's going to the sarcoplasmic reticulum to let the calcium out, and the calcium's binding troponin and pulling the tropomyosin out of the way. And then the actin and myosin can come together, and the actin can pull, or the myosin can pull on the actin and shorten the muscle fiber and make a contraction happen, produce a force. So yeah, that was a lot that went on in this 5 millisecond period of time, but there was not 1 millivolt of force being produced, or 1 gram of force, I guess. Not 1 gram of force was being produced during that time. And then as soon as the actin and myosin bind, so we'll put myosin and actin bind, then we get the contraction period. So as long as the actin and myosin are staying attached to one another and shortening, then we're going to get this contraction period. Then as soon as the calcium is pumped back into the sarcoplasmic reticulum and the actin and myosin can no longer bind to one another, then we go to relaxation. And then relaxation will happen until we stimulate the muscle again. So in a muscle twitch, we have 3 periods. We have a latent period, a contraction period, and a relaxation period. And so you can read about those in this picture, which I just described to you. Okay, so now, we're going to come back to TREPA. First, we're going to do multiple or wave summation and multiple motor unit summation. And then we'll come back to TREPA, and then we'll do tetanus, and then that'll be it. All right, so changes in stimulus intensity are going to create, so it makes things heavier. So as things get heavier, when we're trying to lift heavier things, or if we're holding something and somebody's piling things on top of your arms, you have to exert more and more and more force. And some of your muscle fibers are already contracted, holding it in place. Some of them have fatigued and they pooped out, and other ones have to come in and help out. And so that is called recruitment. And so as we're increasing the strength of the stimulus, so as the voltage or the strength or the weight, strength or weight also of what we're trying to, our muscle contraction increases, more motor units are recruited to contract. So we're picking new guys. We're just grabbing motor units off the street and saying, hey, come on, help us hold this thing in place. And so we call it multiple motor unit summation, because we're getting more and more and more motor units in order to hold up the object. Or let's say in the beginning, our brain decides how many motor units to recruit before it even picks up something. And so that, like it says right here, this explains how muscles exhibit varying degrees of force. So when we recruit just a few motor units, then we're just going to lift something light. But if I want to lift the suitcase with the same muscles, I am going to have to use more motor units. I have to call more muscle fibers into play. But we're only going to recruit whatever number we need to do the job. So if you think about, let's say that you have your flask of water. And so you had your flask, you fill it up with water, and that's kind of heavy when you've got your flask filled with water. And then you set it down on the counter and you left the room. And then someone comes along and dumps all the water out of your flask and puts the lid back on and sets it back in the exact same spot. You come back in the room and you go to lift that flask thinking that it was as heavy as it was when you put it down, that was full of water. And so your brain picked, let's say 20 muscle fibers to lift that water bottle, but now it's empty, so you only need 5. Well, you already picked the extra 15. You've already picked 20 and you only needed 5. So what happens to your water bottle? Yeah, you like smack yourself in the face with it. So when you recruit lots of muscle fibers and you don't use them for force, you can use them for speed instead. And we'll talk more about that when we get into the different types of muscle fibers in your body. But the point is that your brain decides how many motor units to recruit, and then it picks those and uses those, even if the thing wasn't heavy and you didn't know it. Okay. And when we recruit, we're going to pick the small ones first and the larger ones last. So we have small, medium, and large. So we're going to pick the small ones, and then if we need more, then we'll use the large ones if we have to. Okay, so here's what's going to happen is that I'm going to exert a force, little muscle twitch right there. Oh, all it took were 2 motor units. Okay, it only took 2 motor units to do the job, and I got a little baby force. Now, those guys are going to stay contracted because they have to help hold, because now I'm going to add some more muscle fibers. I'm going to add more weight. So now I added more weight right here. So 5 and 6. We can think of these as pounds instead of voltage. Okay. And so now what's that going to take? The 2 that I had already contracted plus 2 more friends. And then the 4 I already contracted and some more friends. And then till finally I get something so heavy that I contract everybody. All my friends are all helping me in my tug of war contest. And so we call that maximal contraction, when all the motor units are contracted at the same time. And we also call that tetanus. So all muscle fibers contracted. And so we'll get to more about tetanus in a minute. Okay, so multiple motor units. And this is just a great representation. So here I just used 2, now I use 5, and then however many that is, and so on until they're all being used. All right, now that's not the only way that I can increase the force that a muscle produces. So the second thing that I can do is called wave summation or temporal summation. When I stimulate, so I change my stimulus frequency. So I stimulate faster and faster. Okay, so here we've got about 20 stimuli per second. And what we can't do, if we're stimulating 20 times a second, we can't relax between the stimuli or between the twitches. And what that does is allow the force to add up to produce higher tensions because the muscles haven't completely relaxed before it's time for them to fire again. So then we're going to get things called complete and incomplete incomplete tetany and complete tetany, or fused or complete. Okay, so let me show you how all of this works. So we take a look at this picture. I stimulate it, muscle contracts, relaxes, goes back down to normal. Then I stimulate it again. I get the same contraction back down to normal because I'm stimulating it with the same amount of force and I'm not stimulating it very quickly. So then if I come over here and I stimulate it and my muscle force goes up and then it wants to contract back down again, it should go all the way back down to 0. But look at what I did. I stimulated again. Now, this isn't like absolute refractory periods where the muscle hasn't repolarized. It's repolarized. It just hasn't gone back to its normal resting length. So it can receive an incoming stimulus. So it's not going to go back down, completely back down to relaxed before we stimulate it again. So now, since some of these guys produce this force, now I'm going to add to that some more force, keep these guys contracted and add a bunch more. And now I get an additive force. So I get it even stronger. So now let's stimulate it even quicker. And every time I stimulate it, I'm going to get an increase and increase and increase in my force. And that's known as wave summation because I stimulated it faster and faster and faster. Now, what if I'm stimulating it so fast that it tries to relax just a little tiny bit, but I still have about the same force? My force really doesn't decrease very much. Then I call it incomplete tetany or incomplete tetanus. Okay, now it's not like the disease, but kind of like the disease. Because when you have the disease tetanus, it does get you to the point where all your muscle fibers are contracting at the same time. This incomplete tetanus is like, let's say that you're holding something up, like you're holding your arms up. So you're holding a building up, you're holding up a building, or you're just holding something above your head. And then you just keep, your brain is sending signals, stay contracted, don't relax, don't relax, don't relax. And then your muscles start to quiver because they want to relax, but your brain says nope. And then they want to relax, nope, want to relax, nope, nope. And so that is incomplete tetanus. But then you get a point where the stimuli are coming so fast, just right on the heels of one another, that the muscle just has no hope of relaxing at all. And that's when we have complete tetanus. And so this is no relaxation at all. And you will stay, if the stimulus is still being applied, you will stay in tetanus until your muscle fatigues or it just runs out of ATP. So runs out of ATP. Okay. All right, now let me show you what tetany or what trepa looks like. So we're just going to commandeer this image and make it trepa. All right, so I can stimulate this muscle, but now that I've relaxed, if I stimulate it again, guess what? My contraction is going to be slightly bigger the next time. Okay, and then I relax, and then I stimulate it again, and it's going to be a little bit higher. And then I stimulate it again, and then it's just going to stay at the same height. But notice we come all the way back down to relaxation each time. So trepa is muscle warm-up. And so what we're doing is that we're stimulating the muscle. Okay, I contracted, boom, I relaxed. But the second time, because I've used some ATP and my muscles are actually physically warmer and more ready to fire, they produce more force with the same stimulus. And we'll do that for the first little bit, and then we're good. So muscles actually do need to be warmed up before you will get the optimum performance out of them. So let's say that you're shooting baskets and you're standing at the free throw line and you shoot the first basket and it just bounces off the front of the rim. Okay, that's because my muscles were not warmed up. And so they weren't as accurate. They weren't contracting with the force that they normally do. So then I shoot it again. Maybe it just kind of hits the front of the basket and kind of bounces around. But then I shoot it again and I swish it. And I shoot it again and I swish it. I am not shooting any harder than I was before. I'm just shooting and my muscles are warm and now they can contract better so that my accuracy is better. And so that's TREPA, or muscle warm up. Okay, so the things I need you to remember mostly with wave summation is that I get a wave summation with the change in stimulus frequency. And then I get multiple motor unit summation when I get a change in stimulus intensity. So that would be strength or weight. All right. Now, if we take a look at the discard. Okay, if we take a look at the last of our list, I have some steps to muscle contraction. And so as you go through the lecture notes and see what does it take for muscle contraction to occur, or if you just look in your book, you just put these in order. So they're all mixed up. So like the first one that you would do is stimulus begins in the brain. So that would become, this top one right here would be number 1. And then you decide number 2, 3, 4, whatever. And until you get to 18. So there are 18 steps. And I do have a key to that in the announcements, but don't go to the key yet. Just go ahead and see if you can figure that out on your own. Okay, let's go to the APR for a moment. Here's the APR code is capital Y, EH, capital R, capital Y. And do that. Let's see. Okay. So when we go to our APR, let me make sure that's, yep, that's go to our APR. Okay, so we're going to go up here to muscle physiology, capital Y, EH, capital R, capital Y. And we're going to go to muscle. All right, now notice that there's nothing in dissection because we're microscopic. So we need to go to my histology. And when we go into my histology, let's look at a myofibril. So here is an entire myofibril. Let me click off the highlight. Okay, so this long tubular thing is a myofibril. And we're just showing part of the myofibril. All right, so let's go to the parts that we want to take a look at. So let's look at a sarcomere first. So that's going to extend from Z disc to Z disc. So this whole area in here. So if we look at Z discs, yeah, those are those dark bands that we find making the borders of a sarcomere. Okay, then we want to look at attached to the Z disc is going to be the I band. So here is the I band. So here's my Z disc in the middle, and then I'm going to have thin filaments go off to the right and off to the left of each one of these Z discs. So those are the thin filament, the I bands or the light bands, and they are just made of thin filaments. So that was okay. And then the A band is going to be in the middle. So here was the I band, here's the A band that has overlapping thick and thin filaments. And then in the middle of the A band, which is made of both actin and myosin, I'm going to have my H zone. So it says H band, but it's actually an H zone. So there's the H zone. And then in the middle of the H zone is the M line. And there's the M line. Okay, so there are all of those. And then you can look at the other pictures if you want, but I don't really care. Then if you go to animation, if you go through all of these videos, that will help you with your steps to muscle contraction. And so that shows you the events, the neuromuscular junction, excitation, contraction, coupling, cross-bridge cycling, and all throughout this. So these are really good videos to watch. Little short animations in order to help you understand the muscle physiology we see at a microscopic level. Okay, so that's it for this video, and let me know if you have any questions.